Last. Oh, there's one more.
Unfortunately.
Well, then thanks for the last lecture, and we'll hear more about CHY and maybe some political.
Thank you. Yeah, I realize it's a big mistake to do three in one day, and maybe if someone want to take my fourth slot, do it. Okay, so it's kind of probably I'll go to the idea of doing forms, not geometry yet, but forms, which is very natural from the CHY point of view. But before I go there, let me just briefly summarize what we did and what are the extensions and say interesting open questions just before I go to the more differential form and geometry world, which really will be the topic tomorrow for the associated hedron and so on. So we essentially set up this scattering equation based formulation that you can write down integrals over modular space localized by scattering equations, which are actually summing over solutions for various theories, and we see in the end that many properties of those amplitudes and especially the double copy can be made manifest. So the last thing we stopped at this point. Let me just rephrase it again, that when you have this, it really means you can write things as double copy in this KLT language, where your KLT kernel now have a nice interpretation as the inverse matrix of the n-3 factorial m alpha betas, right? So here you have I left with Pactator alpha and I right with Pactator beta. So when this happens, we just say, this theory, we start with some theory, is the double copy of the left theory with the right theory, right? So we see that Yang-Mills case, it gives you gravity. And just by doing this, you discover many more relations like that. Say like nonlinear sigma model, double copy with Yang-Mills give you Born-Ingfeld. This is quite surprising. I mean, why is that, right? I mean, I guess there's a recent understanding from Lagrangian now, but when it first comes to us, it's out of the blue. Why would you see that, right? And all nonlinear sigma model squared give you this even more weird special Galilean theory, right? And here there's of course a lot of generalization of this. If you do dimension reduction, as I said, this scalar part of the dimension reduction for Yang-Mills is also very interesting, that it double copy you to this theory we love, the enhanced Adler zero DBI theory, and many other things that I will not come here. So all this is in the context of KLT. You can do the same in the context of color kinematics. Let me just emphasize this very quickly. All you are doing is expanding your I left or I right into Pactators. So this is guaranteed to work because Pactators form a basis of the space of half integrand that do not have that only has logarithmic singularities in sigma. So this is a very crucial point I want to emphasize. If you start with something that has intrinsically some double pole and so on, so so if you instead of having sigma 1 2 2 3 3 4 4 1, this is your Pactator. If you had sigma 1 2 square 3 4 square, this thing is bad, right? So now you have to eliminate such double poles using scattering equations and so on. But the key point is that our Pfaffian and so on never have those things. So they are always intermediate. They are spurious poles in the Pfaffian and in all those half integrand we have. So what you can do is you can take the half integrand like your Pfaffian, and you can always expand them into a basis of not necessarily a basis even, just any Pactator, say beta, with some coefficient. Now it's independent of sigmas. Now this coefficient are only they only depends on kinematics. So if you start with some half integrand that depends on sigma, k, epsilon, and so on. Now this guy only depends on k and epsilon. All the sigma dependents are here. So I want to emphasize this is always possible to do, okay? You need to bring it to the form that has no double poles and so on. But that's a property of our integrand, or our half integrand satisfy this. So once you are there, then the evaluation of your CHY formula is trivial. So if we have the case for partial amplitude, say Young-Mills, or in general, some formula with Park-Taylor alpha and this I that we can expand. Let's call it I right? Now you are literally doing sum over beta and beta of m alpha beta. Right? So I want to emphasize this is a consequence of the fact that you can expand anything without double pole into Park-Taylors. You are in this form. And once you are in this form, it's color kinematics satisfying. Where do you see that? So this guy, as I said, you can further write down each of them in, for different betas, you can write them in, you can write it down as summing over cubic graphs, right? Now, for each cubic graph, its numerator is now given by some combination of n beta, which automatically satisfy Jacobi. So you can say that this is one easy way to see it. And now if you, let's put a right subscript in here. Now if you do it with gravity or in general, some formula like that, it automatically gives you sum over alpha beta and alpha of left and beta of right, and then m alpha beta. And this is nothing but the BCJ double copy of the thing you start with. So let's do a 4-point example. So say for example my amplitude 1, 2, 3, 4 that has a Park-Taylor 1, 2, 3, 4 here and some I right that I can expand. Let's say we expand this I right 4-point into Park-Taylor 1, 2, 3, 4 with some n, just with some a, and then some Park-Taylor 1, 3, 2, 4 with some b. Okay. Now you can just evaluate your amplitude. Let's do quite n of s, n of u. It doesn't matter. You find two coefficients, right? Now you plug it in, and remember that the 1, 2, 3, 4, 1, 2, 3, 4 for this guy is just n is just 1 over s plus 1 over t, right? From our example before, and this guy is just what is it? Minus nu over. This guy is just 1, 2, 3, 4, 1, 3, 2, 4 is just minus 1 over t, right? Yes.
So this means we never actually need to solve the scattering equations, and you can always just expand any integrand out in terms of the biological.
Exactly. Yes. Yes. That's how you actually evaluate your formula. Of course, these ends are not unique. Once you do this, of course, you pay a price that now you don't see it's gauge invariant, right? You know it's gauge invariant because it starts from something that's gauge invariant. Now you are going to something, unless you go to a minimal basis, now the ends can be, in the minimal basis, they are gauge invariant again, but it's like a tautology there. You're expressing them in terms of partial amplitude again. But I'm just saying this can be any set of beta. It's not a minimal basis, so there are many ways to do it. But find any way of writing your half integrand into Park-Taylor with some coefficient, then you're done. You are done evaluating your CHY formula. And this is obviously satisfying Jacobi. If you do also other orderings, I didn't do it for you, that you have ns over s plus this ns minus nu over t. And this is something you recognize that you should call it nt actually, right? So in other ordering you will see it. And then this one, the double copy one, m4, will be just given by, if you plug in what I just did, it will be given by ns square, or generally ns tilde plus nu square, and then there's a cross term that looks like ns minus nu square over t, but that's exactly what you need to double copy. So all I want to say is that once you have CHY formula for it, then this is the way you extract numerators that satisfy Jacobi, and then the formula that double copies it in the CHY sense also double copied in the BCJ sense. Just to finish up what was left over. So this applies also to other pairs of double copy, right? Okay, so what are the interesting things that we can do further that, or at least things that I didn't cover here? I didn't tell you how to where all this come from, right? So one way to see, I mean, there are many things. So one thing that I didn't cover is this ambitwister string, which is a very nice framework of deriving all the CHY formula based on some string theory that's not the usual string theory. The string theory that has no alpha prime in it. So essentially, when you write down the this ambitwister string, in the part that analog to the Polyakov action, you already impose. They already naturally impose scattering equation. So there's only the massless excitation, and the string integral you write down already have the delta function with scattering equation. And now if you put in different matter part to your action and cook up the vertex operator, they will give you Pfaffien or other things I discussed before. Okay, so this is a framework. At least at tree level, it's reproducing you everything that I said here. Of course, now you ask a deeper question where this comes from, and I don't think anybody has a good idea about that. So this is something you can construct, which naturally it's OPE and so on lead you to CHY formulas at tree level. But now you can do more. You can compute the same thing at higher genus. You can do higher genus Riemann surfaces, and again you run into a problem already at one loop that you don't know how to evaluate. Actually, I think it's safe to say that we still don't know if the one loop ambitwister string for different theories can work. Something that a lot of people believe that will work is for the special case of supergravity in 10 dimension. Then you can write down an ambitwister string, ambitwister model on the torus that seems to be consistent. And if it's as these people claim that it's by the way, this is work of Mason and Skinner and their collaborators, quite a series of work starting 2013. That if the claim is correct that this model for at least the model for supergravity is modular invariant at one loop, then you can do the trick of taking the degeneration limit, and then the ambitwister string degenerate to something that's much more manageable. This model is based on nodal Riemann spheres, right? So instead of study torus and things which are inevitable in string theory, here it seems you can take a shortcut, at least at one loop and two loop level for the supergravity case. You can really degenerate everything to Riemann sphere with more pairs of punctures, and now you can compute your analog of one loop scattering equations, one loop Pfaffiens, and so on. Okay, so this is the status of loop generalization. I wouldn't say it's a complete story here, but there's at least this generalization of the formula I talk about to one loop and some cases to two loop. So you can understand them from other point of view if you ask me later, like forward limit and so on. But this is one thing that I didn't cover. There's actually a very nice very nice workshop just happened in April at Perimeter, where there's some pedagogical lectures on this subject, not just CHY but also this. So if you want, you can refer to those things. The second thing I wanna say is the connection to actual string theory, amplitude. And here it's actually also, yeah. So this is another interesting subject that we still don't fully understand why CHY formula come as the field theory limit of string amplitude, but there's already a lot of things you can play with here. For example, the double copy idea has been generalized by Oliver Schlöter and the collaborators into string theory, that you write your string theory amplitude in terms of double copy of some field theory and then some stringy object like this so-called Z integral, Z theory, which is something that has alpha prime expansion, but it's much simpler than your usual string theory. In that context, you can also do all this CHY business for the string integral, and there are other generalizations to bosonic string, very recent works by Oliver Henrich and collaborators. There's a lot of things to be said there. And the third, yes?
Do I understand correctly that they really did this only at tree level?
Tree level, yes. This is I'm still talking about tree level. Even here, I think it's not a fully understood problem. I mean, it's also connected to the Let me first continue. There's the connection to the more mathematical side, especially with this geometries and so on. So this will be the topic I want to continue here. So I think there's a very natural framework of putting CHY under the same. So in other words, what I've been talking here, you can now view it in a more geometric sense once you consider the idea that you don't want just study rational functions for your amplitude, but rather you want to study some differential forms living in this kinematic space. And then CHY will have a geometric correspondence there, have a geometric origin there as some map from moduli space geometry to your kinematic space geometry. So this is a direction that I want to focus on for the remainder of the lectures. And of course, there are many other things. You can go down to special dimensions to consider 4 dimension. You go back to the twisted strings formula I said. There are 6-dimensional, very nice formulas in 6 dimensions for theories in 60, and there are a lot of extensions of things I said. But let's now focus on here. And I think eventually one of the goals in this line of research is not just to do field theory with CHY and so on, but also to recover string theory. So we want to see to what extent we can discover string theory, at least in certain sense, discover string theory by considering such geometric questions in the modular space. So in some sense, we will. So in the next 1.5 lectures, you will see how we discover CHY as a geometric statement. But that's only the field theory, right? The final goal is maybe we want to study. We want to find the full-fledged string theory as some natural extension of the geometry that we study here. Okay, so what should I do? So I think I promised basically that tomorrow's lecture will be self-contained. So I won't directly tell you the things about geometry and so on, but I will start by considering something very simple. So instead of doing CHY formula, is there a way of just considering half integrand and find something for that half integrand? So far you've seen that CHY is like the amplitude is like a product of things, right? You take I left, I right, and then you find something come out as a rational function in your kinematic space. Wouldn't it be nicer if you can give meaning, some amplitude like object in the kinematic space for every half integrand rather than a pair of them? So that's another motivation. Not talking about geometry and anything. Another motivation of considering differential forms. Okay, so let me just do that. As we already said, the half integrand transform as this weight 2 thing, but it's really natural once you consider them as a form. You don't need two pairs of things. You just write down, say, Park-Taylor 1, 2 to n. This is not SL2 invariant, it's only covariant as weight 2. But now if you put in this d n sigma over SL2, you call this some form, omega. This is an n-3 form because you only have n-3 integration variables here, right? n-3 d here. So it's some n-3 form with an ordering. This is now SL2 invariant, because it cancels the weight there. So my question is there something natural you do to this object that gives you something in kinematic space without talking about the whole CHY, which comes like a pair of things? Okay, so this is of course later we'll realize this all comes from geometry. But now let's just study this interesting. So by the way, this object is connected to many things. So it is, if you write it, you can really easily write it as d log of, say, let's even fix sigma n to infinity. Do we have to do that? Well, let's see. One way to write it is like that, okay? n minus 2, n minus 1. So you can write it like that. You can put back sigma n's to make it across every entry a cross ratio, right? But for simplicity, I just send sigma n to infinity. This is actually your the form that corresponds to Park-Taylor. So it has another. Once you write it this way, it has a very natural interpretation as the so-called canonical form of a positive geometry. So I realize that I haven't explained either terminology to you. So let me do the following. So far, in all things we've considered, we are doing the complex modular space, right? But to make things simple here, because we're going to take, all this CHY formula is like closed stringy, like you have I left, I right. Now we want to do something open stringy like. We don't want to just take a pair of things and do the complex integral and so on. The localized integral, but in the complex modular space. Now we want to just see this object. So it's very natural to consider the real part, actually. Okay, and what is this natural space you consider? Is M0 and R now, not C. And this guy just describes you the modular space of n ordered points on the boundary of a disk, right? You put one. I mean, you can put any ordering. So the whole space is tiled by a different part that has a fixed ordering. So let's focus in one of the part with this ordering. Okay? So this is the part of your real modular space that describes n ordered points on the boundary of a disk mod SL2R. Okay? So this space is very interesting. I think it's, yeah. We can spend a little bit of time study this space, and it turns out the canonical form of this space is this Park-Taylor form. The canonical form means that you can define some differential form on. So the modular space of this is a positive geometry in the sense that it has. What are the boundaries here? The boundaries are just when these sigmas start to pinch, but only in this ordered way, right? And they correspond to singularities of our Park-Taylor factors, say sigma 1, 2 pinch or 1, 2, 3 pinch together, and so on. So we want to write down a form that has logarithmic singularities on all the boundaries of this space. And it turns out it's this form. I won't go into too much detail, but you can really just check that when you have, some singularities are trivial. When you have two punctures, like sigma I goes to sigma I plus 1, obviously it has the pole and logarithmic singularity there. But it's also, when you have like sigma 1, sigma 2, sigma 3, all three of them pinch together, that's also a codimension 1 boundary of your space. This guy actually also has a logarithmic singularity. Okay? So this is the form that has all logarithmic singularities on boundaries of this space. And this space has a polytope interpretation. It's a sociohedral. So this is also a cool fact that maybe I can explain tomorrow more about what a sociohedron and so on. But right now I'm just saying there's a lot of motivation. You can study this object. It's also related to the positive Grassmannian. Okay, so this space is nothing but your familiar G plus 2n. Now mod all this GL1 torus action, right? You can mod out n minus 1 of them. So if you start with your Grassmannian, which looks like this, that you have, say, lambda 1, all the way to lambda n. So this space has all the minors positive and so on. Now if I mod out all the GL1, I end up with this space of sigma 1 to sigma n that are ordered. And now also with an SL2, right? Here you mod out GL2. But then after modding out further all the GL1s there. So it's all connected. So if you take Jake's top form of the G plus 2n, you mod out all the dt over t, the trivial GL1 factor, you get this factor. So this is our Park-Taylor. His Park-Taylor turned into our Park-Taylor, which starts as a 2n minus 4 form, now it's an n minus 3 form. Okay? So these are just some motivation for considering this form. Now you can do something very cool about it. Forget about all these integrals and so on. You do something that we call push forward. But really, it's just a simple operation of taking the form. So remember, this is a form now it has sigma and also d sigma in it, right? It's all everywhere you have d. Now, literally, you just plug in the solution that sigmas. Now you can solve the solution of scattering equations. That the solution will be sigma equals some complicated function of Mandelstam and so on. But you just plug it in. Okay, you plug in all the solutions and sum them up. Remember, when you plug it in, when d hits on these sigmas, now they hit on the Mandelstam, right? So they become it's still a form when you plug in the solution. So on this side, you just get a n-3 differential form that now depends on Mandelstam and d of them, right? So this is a very natural operation because you put the d there, you make this thing SL2 invariant. Now you can forget about all the scattering equation integral with delta function and so on. You're essentially doing that, but now just for one single half integrand. You can just instead say, I want a sum over solution of this form, then you get another form here. It's guaranteed that this form will be some rational thing in Mandelstam after you're summing over all solutions, right? So this is, I think, another motivation, even before you touch geometry and so on, to consider differential forms in kinematic space. In particular, this differential form. What is this differential form? That you take your Park-Taylor form, it's obviously cyclic. It should be cyclic because you took something that's cyclic. You just summing over all the solution of your scattering equation, you get some differential form here. And because of the fact that this guy is d log, you're expecting, this guy should probably also be d log of your Mandelstam variable, right? So this is an interesting question by itself. Instead of considering closed string-like object in CHY, you just do this. And now you can do other things. You can do Pfaffian. You can just take a Pfaffian and do this. Sum over solution, you'll get a form. That form should be relevant for Yang-Mills because it has polarization and so on. But what is that form? It's so counterintuitive. We always consider amplitudes as a rational function in a kinematic space. But now they are very naturally come as a form. Once I consider only half integrand, not a full integrand. I want to do something SL2 invariant, right? So let's do a quick example. Say if I just have 4-point. It's essentially the thing we did before. So for 4-point with the gauge fixing, say also sigma 1 is 0 and sigma n minus 1 is 1. So what is this form? It's just a one form, d log of sigma 2 over 1 minus sigma 2, say. Okay? Now if you plug in the solution, if you still remember, in this gauge fixing, it's probably s over u with a minus sign. You can do it. The sigma 2 term, it's d log of s over u with a minus sign. But now if you plug in the denominator 1, what is that? T over u with a minus sign, I believe. So this is nothing but d log s over t. If you want, you can also write it as ds over s minus dt over t. Okay, so this is our first example of a push forward, that you start with some form in kinematic space. You just plug in solution of scattering equation, you get some form in Mandelstam. They're interesting things. This is a cyclic thing up to a sign. And it looks like our phi cube amplitude, but not quite, right? Our phi cube amplitude was, at least for the planar ordering, is 1 over s plus 1 over t. Okay? Now you say, let's turn it into, we want to write down a one form. What could you do? You just turn it into ds and dt. But now you are not sure about this sign, right? Now you can put plus sign or minus sign. It turns out this minus sign is quite important. So that you can do it for any number of points. There's this beautiful statement which has a geometric origin that maybe I'll come to it tomorrow or maybe later today. So when should I stop?
You have 20 minutes.
Great. So let's write this down. So if you have Park-Taylor 1, 2 to n, if you have that omega that I defined, 1, 2 to n, is an n-3 form. And if you do the summing over solution thing, you get something that we call the planar scattering form. So now it's not a scattering amplitude, it's a scattering form, which is nothing but summing over planar graphs. Okay? So just like when you do m, 1 to n, 1 to n, it's only summing over planar graphs. But instead of just putting S1 to Sn-3 of that graph, you put also the ds here. Okay? It's kind of really the very simple generalization. The only thing that matters here is there could be a sign. So you can have a sign of graph G. Okay? So this is really wedge product. Sign, of course, depends on how you wedge them together, in what order you wedge them together. But this is something you can actually prove. And what's the rule of that sign? It's also very interesting. It's really has an idea. It has something to do with this mutation. So here you can view your 4-point example that, like, if you start with a S-channel diagram, when you go to a T-channel diagram, you did a mutation in the sense that, well, in this case it's particularly simple. You keep everything else unchanged and you flipped one propagator, right? So this is what we mean by a mutation here. So in general, if you have an n-point cubic graph, if you keep n-4 of their propagator unchanged and just have one propagator go from like S-channel to T-channel, this flip, your sign should change. So this is the rule. So this is the result that if you take particular form summing over all solution, you get this. Okay? Yes?
How do you actually do the sum over solutions?
Yeah. I'll come back to it. So obviously you don't really solve them, but that's the result. So let me see what's the best way to do this. So this form has a we can also consider something from the without CHY. We can consider this form independently in an interesting manner. So it turns out in the end, this form is the canonical form of a pseudohedron in the kinematic space, which now it lives in the space of all the Mandelstam, all the Ki or Kj if you want. And now you can do some, you can make some inequalities and carve out a polytope. This guy will be the form that has logarithmic singularity on every boundary of that pseudohedron. So, but as I said, I'll focus more here on the form side. So, what is the property that defines? So, forget about it comes from CHY. If I just want to write down some form, why would ds over s minus dt over t make more sense than ds over s plus dt over t? Okay, so now it's clear that we are dealing with logarithmic d-log form, so we don't want to put arbitrary coefficient here. The coefficient are just plus minus 1, right? But still, what determines this sign, this relative sign? If you do CHY, it tells you it's minus sign. But is there a priori, is there some rule tells you that it should be minus sign rather than plus sign? In this example, clearly there's a rule. I mean, you don't know where it comes from again. Now we understand better where it comes from, but it's very natural. It's just asking the following. So if it's a plus sign, then the form has pole at infinity. In other words, it's not we call this property projectivity, or the fact that you can define the form in a projective space. It's well defined in projective space. So if it's a plus sign, then you cannot write it as ratio of Mandelstam, which makes sense in the projective space, right? So if it's plus sign, it depends on actual S and T, not just its ratio. So in general, we want this property. We want S and T when you do a rescaling, but a local rescaling. This rescaling itself can depend on S and T of S and T itself. So you scale S to lambda S and T to lambda T. You want the whole thing to be invariant. This is the essential property that fixes this thing. In the 4-point example, it's really simple. It tells you this has to be minus sign, but this turns out to be enough to fix all the signs here. So if you list all the planar graphs there, there's only one choice of the relative signs that makes this happen. Okay? So only for one choice of the relative signs can your form be a projective form. In other words, it only depends on ratio of this Mandelstam. Okay? So this is quite cool that there's this form living in Mandelstam space that is projective. It has no pole at infinity. It only depends on a ratio of Mandelstam. And if you want to see where it comes from push forward of CHY, but it's also independently defined as the only D-log form that's projectively well defined here. Okay? So tomorrow I will tell you how to derive this formula. So actually, this formula comes from, so if you now consider how this formula let's see. Okay, let me do it this way. So now that you have this form, the very natural wondering is this obviously has something to do with our CHY formula before, right, for phi cube case. But what is the precise connection? So now we are writing down some form, doing sum over solution that give you another form. On neither side, we are dealing with amplitudes or rational functions. So how do you come back from forms to rational functions? So this is something I wanna spend some time discuss here. So again, we can go back to 4-point. Okay. Let's go back to 4-point. So when I give you a ds over s minus dt over t, what can you do to turn it into a function? Very simple. You pull back. So this is a form that lives in two-dimensional space spanned by S and T, but it's a one form, right? So when you pull back to some one-dimensional subspace of your two-dimensional kinematic space, it should become some function times the overall thing. Okay, so very natural thing we can do. Say we pull back to S plus T equals a constant. Okay, this is something you can do. In other words, u equals a constant. Now the ds becomes minus dt now, okay? So this whole thing becomes ds 1 over s plus 1 over t. This is your amplitude. I mean, it sounds really stupid. Why would you do that? To first write down this and then pull back to get this. You can do something a little bit more. You can do this, same thing. Now I want to pull back to, say this is u equals constant, right? Now I want to pull back to s equals constant. What do you get? This term drop. So you get minus dt 1 over t. Remember, this is nothing but the m 1, 2, 3, 4 1, 3, 2, 4, right? Well, this is m 1, 2, 3, 4 1, 2, 3, 4. So now you see the rule actually. So you have a form that's tied to the first ordering. It's always 1 to n. It's a planar form. By pulling it back to different subspaces, now I haven't defined you in general what are the subspaces, but clearly the subspace is tied to the second ordering, okay? So in this case, say if I want to recover this 1, 2, 3, 4, 1, 2, 3, 4 second ordering, I need to choose the guys that are not in here. So this contains like s and t, but not u, okay? So u is non-adjacent in this ordering. So I pull back to u equals constant, I recover that. I pull back to s equals, I mean, this example is really simple. Now here comes the general statement that how do I connect back to m alpha beta? So if I start with my omega alpha, that's an n-3 form. As I said, it's the push forward of Park-Taylor alpha with this n-3 d sigma, or it's just the summing over planar graphs where the only set of signs that you can find is by projectivity. So this is something nicely defined by itself. Now if I pull back to some subspace, I will define you now called h of beta. So remember, in general n, you have a quite high dimensional kinematic spaces of this dimension, n-3 over 2. The reason is that this is the space spanned by all the Sij, right? Subject to momentum conservation. So as I said from the beginning, I'm living in some d big enough so I don't have this gram determinant like constraint. So it's just this linear space, n-3 over 2. Now in that space I have a form. I have this nice form that you can interpret as coming from CHY and so on. Now I want to pull it back to some subspace. This needs to be a n-3 dimensional subspace, quite low dimension compared to this. You need to go very, very much down to an n-3 dimensional subspace depending on the ordering. And I'll claim that the result of this is m alpha beta times some overall d volume, say, just a bunch of n-3 ds. This is irrelevant. You just pull it out. The key thing is you recover m alpha beta. So what is h beta? That in this space that defines you a n-3 dimensional subspace. H beta turns out to be, I mean, something you can already learn from this. There are different ways of do H beta, but one way to define it is you already learned it from here. It seems to come from settings Sij's that are non-adjacent in your ordering to some constant, right? So let's just do that. H beta is all the S beta I beta j equals constant for ij non-adjacent. So obviously, you run into problem. So this constant, let me give it a name. Let me call it Cij, or minus Cij. So in the end, if you're talking about geometries, this constant actually need to be positive. There's a positive geometry behind all this. But just today, I just want to talk about the forms. Okay. So you run into problem already here, even for 4 points. So if you do it really carefully, not only you are setting S13 to some constant, you should also set S24 to some constant. And the constant doesn't have to be the same. So now you're in trouble. You shouldn't give 2 conditions. You just give 1 condition. Okay. So there's many ways to do it. A natural way is you just omit 1 particle. You always say, I go to a subspace where ij are non-adjacent, but also it never equals n. So excluding n. This turns out to be the correct counting. So this number of condition, all the non-adjacent ij excluding 1 particle, say n, is exactly the difference of your dimension and the form. It's exactly this number. So this is a nice theorem that you take your form, you pull back to some other ordering with non-adjacent guys excluding 1 particle to be constant, you recover your m alpha beta. Now I can tell you how to prove this formula. So literally it's just some, you know the formula for this one. Okay, so essentially just because this push forward formula implies all the CHY formula for this one, so it must be correct. So actually in this formula you only in the formula for this one you have a solution, sum over solution of Park-Taylor alpha with dn sigma, right? And when you pull back to some subspace, you're actually picking up another Jacobian that turns out to be Park-Taylor beta. And then your summing over solution is going to turn into an integral form with scattering equations. So it's in this way that you show every pullback give you this. So now it's something very interesting that you can check, which is you start with this form that has all the planar graphs in it. By pullback to different subspaces, you are actually killing some of the graph. So like here, right, you're killing, say, ds by going to this subspace. And left with only those graphs that should appear in this m alpha beta. And the next interesting thing is that for those graphs that survive, so either the wedge product becomes 0, for those graphs that you should exclude, when they do survive, they all turn into the same thing, including this sign. So they together with the sign, they make the fact that m alpha beta only has summing over graphs that has +1 coefficient, right? So it's really summing over graphs. So this is a very cute thing that you can check. Like already for 5 point, the examples I showed you for m alpha beta comes in this way. Okay. So this also tells you that the correct way of interpreting such m alpha beta is really viewing them as some degenerate case of the original form. So if this form is the volume or canonical form of some association, then when you pull back to different h beta, you're only seeing some of its facet. So you are only seeing a subset of the terms, while others goes to infinity. Okay, so the reason I didn't want to go to geometry and so on is because in this story, tomorrow you will hear that we have a beautiful geometric story that this guy is the volume of some association in kinematic space, while this guy is the volume of that moduli space, the canonical form of moduli space. And because in the geometry, scattering equations serve as a 1-to-1 map from the moduli space 1 to the kinematic 1, this is guaranteed. So this is a consequence of a theorem studied by Nima and Yonta and Thomas, that if you have two positive geometries, there you have a map that's a 1-to-1 map, as actually a diffeomorphism from first geometry to the second one. Then by summing over the solution of that map, you are pushing the canonical form to the canonical form of the second geometry. Yes?
And the signs are just based by the overall projectiveness, or can you understand the signs?
The signs here, yeah, this is a particular way. So the geometric picture is much more invariant. It tells you this is a canonical form of a association. You can compute in any way you like. The Feynman diagrams, this one that we like most, is actually a particular triangulation of that canonical form, where the signs reflects every simplex in that triangulation is orientation. So you can now understand the sign as coming from the orientation of the simplex. Anyway, those are the things I want to talk tomorrow. But in the last few minutes, let me just tell you, this works exactly in parallel for all other things we talked about, right? So why do we have to restrict ourselves to Park-Taylor? We can do Pfaffian. So let's do Pfaffian with this dn sigma. Remember, if you do this, if you put this form in, it turns Pfaffian into a n-3 form, and this form is now SL2 invariant. So you just sum it over a solution, okay? And then you get a form that we call Yang-Mills form, okay? It depends on k and epsilon, right? So what is this form? It's a very simple generalization of the planar form now. In two senses, that's a generalization. I mean, actually not just for Yang-Mills, but for anything. That this general scattering form is of course always the n-3 form. It's summing over, first of all, the first generalization, not just planar graph, because now you're dealing with something permutation invariant. Why planar graph, right? In general, you're always summing over all the graphs. I hope you know that planar graph, this is the famous Catalan number. And here, you have all the graph that's 2n-5 double factorial graphs. You take the ds, so let me write it, d log s1 wedged to d log sn-3 with some numerator now. Okay, now it's not plus minus 1 numerator. Numerator depends on k and epsilon. So this is, and what are this numerator? I mean, the numerator for that graph. You can understand them as the BCG numerator of that cubic graph. Okay, they naturally satisfy Jacobi identity and so. So sorry, let me say it this way. If you obtain it from pushing forward the CHY formula, it will naturally give you the BCG Jacobi satisfying numerators. But how do you know it if you just forget about CHY again? If you just construct this thing, what kind of constraint can you put on this numerator, right? It seems nothing. You can put arbitrary numerator and it still gives you a nice form. Now you need to go back to our principle here. You want the form to be projective, even in this general case. You want the whole thing only depends on ratio of Mendelssohn, not, right? So in the planar case, it fixes this sign. It says if you have a S diagram, T diagram, it should be differ by a sign. In this case, if it won't fix this, but it will tell you this thing has to satisfy Jacobi identity now. Okay, so that's very parallel to the thing I just discussed. So just give you a 4-point example. So your form is just ns ds over s plus nt dt over t plus nu du over u. It has nothing. This ns, nt, and u has nothing to do with each other so far. It's just a general ansatz. Now if you ask the whole form to be invariant under the rescaling of your Mendelssohn, so the whole form, then it tells you ns plus nt plus nu equals 0. So the projectivity, in some sense, is the reason. I mean, the fact that you want your form to have no pole at infinity tells you their numerator has to satisfy Jacobi identity. Okay, and finally, this form we can again get amplitudes now. Let's just pull it back to a subspace I just defined there, H beta. The result is nothing but your familiar A beta partial amplitude times this n-3 ds. Okay? So really, the color decomposition that we are familiar with by going to a trace of a particular ordering corresponding to pull back your form to a particular subspace with a particular ordering. So in the case of M alpha beta, you can trivially check that this form pull back to H beta give you that, but it's also more general. So in other words, I think it's a good way to think about these forms, at least in the general CHY sense, is you take any half integrand, just with this measure, sum it over solution, you get some form that looks like this is what we call most general scattering form, not just a planar scattering form with this coefficient. So this contains exactly the same information as a color just amplitude, not for a particular ordering, not a partial amplitude, but color just amplitude. Because when you pull back to any subspace, you get your partial amplitude. Okay? So this formula, this formula that summing over solution for Pfaffian give you this form, has the same information as all the CHY formula where you have a Pfaffian and a Park-Taylor of any ordering that gives you the partial amplitude, where all this partial amplitude now come from pullback. Okay, I think my time is up. Tomorrow I'll tell you the geometry behind this. Thank you.
Any questions?
So, another question. So really, this stuff, this M0n, can be quantized and
Oh.
has Poisson structure.
Uh-huh.
And it seems that this means that on this kinematic part, you also should have Poisson structure, and maybe it is related to the three
The Jacobi like yeah, that'd be interesting. I don't know. Yeah. The M0n we consider is naturally just with Poisson structure. You're saying.
Yeah, that's because it
Right.
can be quantized that it
Right,
is
right.
Grassmannian 2n.
Mm-hmm.
So therefore there is Poisson structure.
I see. I see.
It should go to
Yeah, that'd be very interesting to understand. Yeah.
Okay, if there are no further questions, I think there will be a quick break before Jake starts his tutorial. 5-minute break
Okay.
before we see Mathematica live action.